we were talking about match filters for the case of white noise, that is signal in white noise and signal in non-white noise. In the later case we call it the whitened match filter, right, because we can think of the match filtering operation as composed of first whitening the noise and then filtering it for maximization of the signal to noise ratio, right. In any case, the main purpose of the match filter we saw was to maximize the signal to noise ratio at the sampling instant, and the manner in which it achieves this objective is by weighting the different frequency components in accordance with the signal to noise ratio present at those frequencies. That is, those frequency components which are dominantly consisting of signal as compared to noise are given more weightage by the filter as compared with those frequency components where the noise is more dominant, right, and this is the manner it achieves maximization of the signal to noise ratio. Also we learned that the output signal to noise ratio is a function only of the signal energy in the case of white noise, that is when signal is associated only with white noise. The actual signal pulse shape does not contribute to the, or does not matter, does not affect the output signal to noise ratio. The only parameter of the signal that matters is the energy component present in the signal duration. Whereas if the noise is non-white, if it is a non-white Gaussian noise, then the pulse shape will also contribute to the output signal to noise ratio and not only its energy, right. So these are a few important things that we learned last time about match filters. Do you have any questions about any of these?
There is a slight problem.
Yes.
The signal to noise ratio which we defined for a case of a white noise,
Yes.
the noise power we take is N0 by 2. So
N0 by 2 is the noise power spectral density.
yeah, exactly, that's the point, sir. I mean,
Right.
that's what I'm confused.
Yes.
Like signal power we take is A square, into constant, because the filter is effectively S of conjugate of T. So the noise power should be actually N0 by 2 times the bandwidth. But we take N0 by 2 only, so that we get something like
it is actually built in. If you remember, the expression for the signal to noise ratio, output signal to noise ratio that we achieved, that we derived, was actually 2 e sub p. This is the expression which is more educational.
N0.
Upon N0.
But this was derived from A square upon sigma square. Where sigma square we took as N0 by 2. That is the problem.
The other expression is slightly misleading because it doesn't bring out the energy, it doesn't bring out the units properly. This is the one which brings out the units properly, because this is energy, which means actually A square into the time duration, right? Which is probably implicit somewhere in our somewhere. Where did we implicitly use it? Did we say something about the signal energy being unity or something? No, not.
We use the fact that the pulse has the energy equal to either 1 or EP.
Right. So we said that f squared t dt is equal to 1, right? So which is essentially saying that, because if or let's say this is equal to a square, right?
So the point is, when we substitute in S upon N for sigma square, A square comes from A square equal to
No,
EP.
what is the problem that you are facing in your mind?
So sigma square shouldn't be replaced by N0 by 2, but it should be replaced by N0 by 2 times the bandwidth.
The bandwidth is implicitly built in here. That's what from this expression it is not obvious, but from this expression it is obvious, as you can see, because this is signal power times, what is energy? Power times the pulse duration, right? And that is N0 by 2. So if you bring it down, that's N0 by 2 into 1 by T. That's equivalent to noise power spectral density multiplied by the bandwidth, right? So it is, really speaking, this expression is nothing but the signal to noise ratio in the bandwidth of the match filter, because effectively the bandwidth of the match filter will turn out to be 1 by T. So it's built into this expression. It's not very obvious from this expression that we wrote otherwise, but if you really interpret the signal to noise ratio properly, which I tried to tell you last time, it is really speaking the more fundamental expression is this expression, right? The output signal to noise ratio of a matched filter in the presence of wide Gaussian noise is 2 EP upon N0, where E sub P is the pulse energy. Okay.
So if you bring the T down, the denominator we have an energy term, and the numerator we have power term.
No, we'll have power only.
No.
This is power spectral density multiplied by bandwidth, which will give you the power in that bandwidth, right? And which is the power which will really be which will appear at the output of the match filter.
So roughly. How does that bringing that T in the denominator?
Yes.
I mean, how does that T correspond to the bandwidth? 1 by T doesn't correspond to the bandwidth.
It has a units of bandwidth. I mean, it has a units of frequency. Let's put it that way.
So
it's a power. I think one of the problems that he implicitly was facing was the units, although he didn't say so.
Okay, the units are fine.
Right.
But I mean, the problem still remains that N0 by 2 should be N0 by 2 multiplied by the bandwidth.
It is.
How does the bandwidth factor still? I mean.
Okay. This is a mathematical expression we have derived, and an approximate way of interpreting it is like this. That is, it is the effectively signal power that is being put in divided by the noise power in the signal bandwidth. Because roughly for a signal of duration t, we have already discussed many times, we can say most of energy will lie in a bandwidth of 1 by t, right? It's from that point of view, from an interpretation point of view, roughly speaking. Any other question? So is that clarified, Dipankar?
Yes.
Now I'll start by discussing some further properties of match filters very briefly, some of which are more or less obvious to you. So let me discuss a few important other properties, and then we'll go on to use of match filters for optimum demodulation or for demodulation of digital modulations. So some further properties. The first thing to note is, and that we have been in fact just talking about it, the signal output ART, this is the signal output, and we are sampling this output at t equal to, let's say, 0. It could be anything, it could be t equal to some arbitrary time instant t sub 0, but if we choose that equal to 0 without any loss of generality, corresponding to the match filter ht equal to, or was it gt, s conjugate minus t. If it was t sub 0, it would have been t naught minus t. The sample value at t equal to 0 is given by, corresponding to the noise component, equal to, is given by a, the sample value. Its power is a square, energy is a square t, right? Whatever. Actually, the t somehow normalized in my discussion, although it didn't explicitly turn out. So you could say that EP is equal to a square, and I think t is probably implicitly taken to be 1 or something. I don't know how it has come about, that t equal to 1, but somehow the way we have been talking about things, we have made EP is equal to mod a square. In any case, the signal amplitude at the output at the sampling instant is a, right? And the second thing is that the noise variance sigma square at the output, can you say anything about the noise variance? It is equal to n sub 0 by 2. Okay. Actually speaking, okay, I'll come back to that. And thirdly, these are the three properties I want to discuss together. Let me just mention all the three of them first. Suppose you have suppose you have two match filters, both of which are matched to two different pulses which are mutually orthogonal to each other. So filters match to orthogonal signals will individually produce, suppose the input signal contains one of those two signals to which these two filters are matched, and they are simultaneously, this input is simultaneously fed to both these matched filters, right. You have, let us say, signal SOT, S sub OT and S1T, and let us say the input signal is S sub OT, and you are simultaneously feeding it to both the filters, and mind you, S sub O and S sub 1 are mutually orthogonal, right. Then the outputs, the noise components of the two outputs of the two filters will be mutually uncorrelated, right. So the noise outputs at t equal to 0 or t equal to t sub 0 would be uncorrelated, okay. And I have shown this in the form of a picture, whatever we have discussed just now over here. Let us look at what I am saying is, suppose the input is the signal S sub OT plus NT, right, and you are passing it to simultaneously through two different filters, match filters, one matched to S sub O and the other matched to S sub 1. Alright, these are the two match filters, impulse responses of two match filters, and we are assuming that S sub O and S sub 1 are mutually orthogonal, right. And now sample the output at t equal to 0 here, sample the output at t equal to 0 here. The three properties that I have talked about are summarized here. For this filter, the signal output will be A. The noise variance is N0 by 2, okay. For this filter here, what will be the signal output? Is it obvious that it will be 0? Is it obvious? From which discussion does it become obvious? This is a discussion of the previous day's class. If you remember, we also could interpret the output of the match filter as some kind of a autocorrelation function of the signal. In this case, it will be a cross correlation function between the input signal and the other signal, and that we are assuming to be 0 because we are taking the two signals to be orthogonal to each other. So you can prove it very easily that the signal output will be 0 here, but the noise of course will come out in the same way as over here with a variance N0 by 2, right, and therefore these are the first two properties. The third property is these two noises, although they have the same variances, the same amount of power in it, they will be mutually uncorrelated. That is, the noise values coming out here at the sampling instant and the value coming out here will have no correlation with each other. They will turn out to be totally different from each other, right, or will have no correlation with each other. That is the only way to put it. If in addition the noise is Gaussian, that will also imply that they will be statistically independent. The noise values that you will sample, although they have the same variance, will be mutually correlated, and in the case of Gaussian noise will also be independent. So this is the summary of the three properties that we discussed. As far as units are concerned, if you compute the energy over t seconds, this will be a square t, the corresponding variance will change by N0 by 2t, right. If somehow this is implied here that we are considering t equal to 1, but if t changes from 1, then this will become output will become a times square root of t, and this will become N0 by 2t and so on, so that the ratios will remain the same.
So how do we say that the noise are uncorrelated? So
yeah. So let me discuss that now. As far as the first two properties are concerned, let us first talk about that. First property is obvious, that the signal output here will be A and here it will be 0. I do not think I need to discuss that in the light of what we have discussed earlier. This is obvious to all of you. Let us first discuss the noise variance. How is it equal to N0 by 2? Can you tell me how it is equal to N0 by 2? So I am taking the second property now, sigma square.
For that, could you sampling instant was 0 here.
Yes, the sampling instant is 0.
So if it is t0, then you say something.
So output is a by root t.
A by root t, nahi, A into root t.
So t can
What is
Because this was the same point that we discussed a couple of minutes ago. Here, the output is really E sub p, right? Right, and E sub p is a square times t, right? Actually, the output is square root of E. This is the output power. This is the output power, and therefore the output amplitude will be square root of this, which is what I was talking about.
EP is equal to a square.
Hmm?
I think EP is equal to a square instead of a square to p.
Yeah, that is somehow, this is what I was trying to correlate for you. I think I'm also getting mixed up in this energy normalization business. Okay, I'll clarify this point later. I think I'll make it very clear, because somehow this point has to be linked up with the other point that I've been making, that s square t equal to dt equal to 1. I'll come back to this point. I think I've mixed up this point a little bit. It's a matter of just taking care of a scaling factor, which I'll do for you separately. Let me not digress from this discussion too much. I'll come back to this point and clarify this at some point. So let's look at sigma square. This is the output noise variance I'm interested in, which is going to be, we have already seen, the input power spectral density function multiplied by the transfer function of matched filter. What is the transfer function of the matched filter? S conjugate of F. And we have, of course, as far as noise power is concerned, we should only multiply it by mod square of that, right? So we can as well write SF mod square, right? And since we have taken again that particular assumption comes to the picture, and since we are considering white noise now, this will become N0 by 2, this, and since we have assumed that the signal energy is unity, right? So this simply becomes equal to N0 by 2, right? Signal power is unity or energy is unity. Oh, okay, I think that is, yeah, I think it's, that point is also clarified now. We have been talking a bit confusedly about things. I think we should clarify that once for all. When I do this, what is this? This gives you power or energy?
Power.
This gives you energy. This gives you energy. So when I'm saying that integral s squared, let's say it is between 0 to t, is equal to 1, right? It's effectively, we are saying that the signal power, signal energy is unity. So I think that is a point to note. This a square therefore is not really power, it is energy itself. So that's why it's, we have taken it to be equal to a square is equal to E sub p.
in that case, then that problem.
No, we still, we can, I mean, this is, the fact that it is energy still implies that it can be written in this fashion, that it's power times the time interval, right? So all the interpretations are still valid. So I think let's stick to this, and then we'll not bring in this root of t anywhere. All right, we'll not bring in this root of t. Okay. Now the third point which Vivek had asked, how do we say that they will be uncorrelated in this particular case? That is, when you pass the same signal to mutually orthogonal matched filters. I call them mutually orthogonal matched filters because they are matched to mutually orthogonal signals, and the corresponding output samples at the sampling instance would be uncorrelated. Let's quickly look at that. Let's take the third property. What is the noise? Let's write down an expression for the noise output. It will be equal to let me call this n sub o, right, or just call it n prime. then this will the input noise convolved with the impulse response of the match filter, which will be GT minus zeta d zeta. Alright. Of course, and we are interested in looking at the noise samples at a specific time instant corresponding to t equal to 0. Alright. Let me call this for one of the signals, for one of the filters, let's say the first filter I will call it n sub 1, and for the second filter the output at the same sampling instant I will call n sub 2. Alright. So what will be the expression for n sub 1? It will be n zeta, and of course G is your S1, or alright, let's say S1. Yes, conjugate also.
Zeta B.
And I have to put t equal to 0.
Yes, sir. Zeta.
Alright. And similarly n sub O will
Zeta, it will be positive zeta.
Positive.
Positive because zeta is minus s of minus
S of minus t.
s star of minus t. So it will be
alright, it will become plus zeta.
Yes, sir.
Alright.
So what's your no, sir? It will be minus
So it is minus zeta, right?
He is saying GT is equal to
G of t is equal to s conjugate of t naught minus t.
It's minus.
right.
And t naught here is 0. So gt is equal to s conjugate of minus t.
Right.
So that is g of minus.
So what we want to substitute is g of minus epsilon or minus zeta. That will be s conjugate of minus zeta. Oh, okay.
So it will become s conjugate t.
It will be positive zeta.
It's okay.
Positive.
Right. And
It's conjugate.
this is the definition of the match filter in time domain we discussed last time. We did. Please check up your last time's notes. You will see it there. Okay. And for the second filter output, input is same, right? The noise input is same, only the match filter is different. It is S sub O. Alright. And we are to look at the expected value of N0 into N1 conjugate. If you do that, it's very easy to check that it will be 0. Let's look at that. Expected value of N0 N1 conjugate, that is a cross correlation between the two noise output samples, can be written as S1 zeta into S0 zeta. One of them will be conjugate, the other will be, well, I'm conjugating N1 star, so this will be without conjugation and this will become with conjugation, isn't it? If you conjugate N1 star, this will become N star and conjugate and S1. Alright, if you take it, so use that. Double integral, and I have taken the expectation operator inside the integral because it's a linear operator, and this will become just a second, there should be something that we have to be careful about when we are using two integrals. Let me call one of them as zeta 1 and the other as zeta O, right? Or maybe zeta and zeta prime. It will be simpler. This will be zeta. It doesn't really matter. So expected value of n zeta into n zeta prime, m conjugate zeta prime, d zeta prime. I have to use two dummy variables, right? Because I am considering two integrals. What is this expected value? This is n0 by 2 into what? This is white noise. So what is autocorrelation function? n0 by 2
So
delta zeta minus zeta prime. Alright, and that obviously now using the properties of the impulse function, we can write this as a single integral right. We can eliminate the zeta prime, we can put zeta prime equal to zeta itself, because that is the only situation where this integral will be non-zero with respect to zeta prime. And what is this quantity? Assuming that the two signals are mutually orthogonal, this is equal to 0. Alright. So this is how the third property comes about. Now this is a very useful property to take note of when we are going to work with a digital modulation scheme which employs more than one signal, right, particularly more than one set of orthogonal signals, right, and we do have we do have digital modulation schemes or signaling schemes which are based on orthogonal signals, and therefore we are going to have to employ orthogonal match filters, and this property will be useful to remember when we are analyzing the outputs of such match filters. Alright. So that was to some properties of match filters, some further properties of match filters, and finally before leaving these properties of match filters, one last point that I like to discuss is regarding passband match filters, because we will have both baseband as well as passband modulations to worry about. When I say passband match filters, I am essentially referring to the situation when our input pulse may not be a baseband pulse, it may be a passband signal, passband pulse, which means it is embedded onto a carrier. Alright. So what kind of match filter we will have? Of course the definition will be the same, but we will also like to appreciate both mathematically as well as physically what how these quantities can be specified and what will they look like. So typical passband pulse we can write as, if you remember, as one having a real part modulating a cosine carrier as well as an imaginary part modulating a sinusoidal carrier at the frequency f sub o, right. So what can we say about the match filter? Well, if it is a real signal like it is over here, it will be simply S minus t, alright, which therefore can be written as SR. So this will be the match filter, this is the passband pulse. This is the corresponding match filter. Just put t, replace t with minus t everywhere. This will remain cosine 2 pi f naught t, and this will become minus si s sub I minus t sine 2 pi. This will become actually plus, right. We can as well alternatively think of the signal st, just to recapitulate for you, as a complex envelope like that, right, isn't it? Corresponding to this, we can denote this passband pulse by a complex signal which is baseband essentially in nature, and the corresponding match filter will then be essentially S minus t, which will be SRT, which will be S conjugate minus t, right. It will be S conjugate minus t, which will be SR minus t minus J SI minus t. Okay. So this is the mathematical description of the passband match filter, both at the passband notation as well as in the complex notation. Okay. Physically, this is I have just illustrated or depicted this situation for the case when SIT is 0, S sub IT is 0. That is, we are considering a passband pulse with only a cosinusoidal carrier to which the baseband pulse may be modulating. All right. So obviously the corresponding match filter will be simply this, because only the first part of it is there, and the output of this I like you to show that the input is this pulse ST cosine 2 pi f naught t. ST is real, and in fact this whole signal is real, and well here also the whole signal is real, but I am making the quadrature component 0 for this picture here, right. I am essentially taking ST equal to SRT cosine 2 pi f naught t, and in fact I am removing this S sub r also. So I am just calling the input signal as some baseband pulse into cosine 2 pi f naught t. The match filter corresponding to that will have an impulse response S minus t cosine 2 pi f naught t, and this is what I would like you to prove. When you pass this through this, the output will be again a passband pulse whose envelope will now look like this. It is a convolution between the baseband pulse ST here and the baseband pulse S minus t, this modulating the carrier cosine 2 pi f naught t, right. Input is a passband signal, the filter is obviously a passband filter. It is now tuned, it has its passband around f naught, right. It is obvious from here, isn't it? And the output also will be a passband pulse whose envelope will be given by ST conjugate S minus t. Not really envelope here, the output will be this into this, right. Now let me illustrate this. This may be a passband pulse, right. Suppose it was a baseband rectangular pulse. What would have been the match filter output? What would have been the match filter output? It is the autocorrelation function of the input signal, right. So what would be the match filter output corresponding to this? Between 0 to 2t, right. The peak coming at t, right. The same thing when you do in the passband domain, that is when you consider a passband pulse and you convolve with itself, or well not with itself but with its match filter impulse response, the output will be looking like this, okay, with the envelope being the same as corresponding to the envelope of this triangular pulse, which will be a triangle, right, that modulating a carrier of frequency, same frequency f sub o.
Won't the maximum of autocorrelation, the lower case, come at 0 and minus t and plus t?
Well, it depends on where you are sampling. I am taking a causal filter here, but if you are taking the same filter that we are considering earlier, yes, we will say minus t to plus t. That is when we are assuming that the peak occurs at t equal to 0. It depends on where you make the peak occur, right. By introducing delay, I can always make it occur somewhere else, right. So that is really not very important. Absolute time instants are not important, right, for this discussion. If you say 0 to t, then it is better to call it 0 to 2t to keep the causality in picture, but if causality is not a point, then I can write minus t to plus t.
So this is the case for the in-phase carrier only. So what if quadrature is also present?
Yes, this is a very interesting question, and I will just come back to that. The answer is that no matter whether you are considering the in-phase component or the quadrature phase component, since the peak has to occur here, see, in general the output will be, let us look at the complex representation. In general, the output of the match filter will now be complex, that is, will contain both in-phase as well as quadrature phase components, right. But at the sampling instant where the peak occurs t equal to 0, for the complex notation this will be purely real, for the quadrature notation, the quadrature component here will be 0. There will be no sinusoidal component at t equal to 0. It will look like this, but of course the details will change on as you go away from 0. I will talk about this point in a minute. So is this okay? This is how the passband situation will be. The input pulse of this kind will get modified to a pulse of this kind after match filtering, corresponding to the baseband situation here. Right? After match filtering, you will get this kind of thing. Now we could as well implement this passband filter at baseband by first taking this pulse to baseband, that is translating the spectrum of this pulse to baseband by multiplying with cosine 2 pi f naught t, doing baseband match filtering, and then retranslating it back to passband.
What is the need of retranslating it?
If we need the thing, I mean, it depends on what you want, right? If a purpose is to do match filtering of this pulse, right, and to produce the corresponding output, one way is to build a passband match filter with this impulse response. Another way is first to bring the pulse to baseband by down translating the frequency, doing match filtering at baseband, and then taking it back again to the required frequency. Right? It depends on whether this step is required or not. Will depend on the application, right, to which you are applying this.
You show the filters.
Sorry.
You should show the LPF, the low pass filter.
Okay, that's a good question. That will not be required, because after all, what is the purpose of that low pass filter? To eliminate the 2f0 component. That will be eliminated by S minus t itself, because S minus t is the impulse response of a baseband filter, essentially a low pass filter, because ST is a low pass pulse, right? So it will automatically eliminate the 2FO component. That is the primary purpose of putting that low pass filter, to remove the 2FO component resulting from this multiplication. That will be carried out by this match filter itself. So there is no need to show a separate low pass filter. Alright. So finally I will just come back to return to Varun's point that he made by means of a remark, that is, in general the output, let me consider the complex notation. For a passband pulse, I can represent it by a complex input baseband pulse, right? The corresponding match filter will also be a complex valued impulse response, all right? The corresponding output in general will therefore be complex, because it is going to be convolution of two complex functions, complex valued functions. Input is a complex pulse shape, the impulse response is a complex valued impulse response, the output in general is complex, right? But at the sampling instant, what is going to happen? Is it going to remain complex? At the sampling instant, what is the output? We have seen that earlier. Its mod square is a square and its value is a. It's always going to be real. At the sampling instant, the output is going to be proportional to the energy of the signal, right? At the sampling instant, the output is not complex, it is real. So although the example that I have showed you in these two pictures was for the case where the SI component was missing, right? But the fact that it is going to be real at the sampling instant is always going to be true, right? That is, this output is going to peak with a real value at this point. As you go away from the peak, we will have both real and as well as imaginary values, non-zero imaginary and zero values. Of course, then you should draw two waveforms rather than one. The imaginary waveform will go through a 0 at t equal to 0, right? It will be slightly different kind of function, so that when you take the magnitude square at t equal to 0, the magnitude that is contributed largely, in fact only by the real part, and there is no contribution from the imaginary part. So that I hope answers your question. That is, for a general passband signal which has both real as well as imaginary components, or in phase and quadrature components, at the sampling instant the contribution will be only the in phase component, will come only from the in phase component and not from the quadrature component. Will come in the form of a in phase component. The output will be only in phase at that point. Like, of course, contribution will be there from both. Any questions? Okay. So with these properties of match filters in the background, we now come to our main business, and that is demodulation. Before I come to that, if there is any doubt of any kind, let's discuss that briefly and get it clarified. Anyone has any questions on the various properties of match filters we have discussed so far? No questions? No? None? Okay. So let's therefore come to digital demodulations, and the first class of digital demodulations we consider are binary modulations. And so I'll discuss the subject of coherent demodulation for binary waveforms or binary signals. Okay, and it will be kind of convenient to restrict our attention mainly to the passband modulations, although baseband modulation also will consider, because once we have the results or the discussion for passband modulations, the corresponding result for baseband modulations now become trivial, particularly in view of the fact that even a passband modulation can be expressed in terms of a complex baseband representation. So now the general passband waveform, received waveform that you will get at the receiver, in general, we had just discussed a few minutes ago, will be this. Okay. What is the difference? Now I am talking about VT, the received signal, which contains both the transmitted signal plus noise, right? But since we are assuming that everything is around some frequency f naught, even the noise can be represented in the same quadrature form, right? So V sub r contains S sub r plus N sub r, and V sub I contains S sub I plus N sub I. Okay, everything else is same as we discussed a few minutes ago, except for the presence of theta. What does this signify? This signifies that you might have transmitted S sub r cosine 2 pi f t minus S sub I sine 2 pi f naught t, but what you will receive is that plus a phase shift. The carrier will have undergone some phase shift.
Theta will be the same for both cos and sine component.
That's right. So it is same. I have put it same.
Will it be same?
Yes, of course. Because after all, what is this? This is just a quadrature representation. You could as well think of this as some envelope RT into cosine 2 pi f naught t plus theta. Right? This is after all a different way of writing this. Basically, the carrier has undergone a phase shift, and in its quadrature form, this is how it will look like.
So how is the carrier undergone?
This should be theta plus phi t. I'm sorry. The general modulation is given in terms of RT and phi t, right? For example, if it is binary PSK, phi t will be plus minus pi, right? Depending on the input pulse sequence. This is the envelope, which may be rectangular, it could be anything, and it could be represented in the quadrature form like this. The theta is the phase shift that has taken place in the carrier during transmission, right? Yes, so Dipankar, what is your question?
So the noise doesn't affect the envelope.
Yes, it will affect this envelope. Actually, see, it depends on what you are talking about. If this is purely signal, then this will be purely signal attributes. But if it contains both signal and noise, then those attributes will also appear here.
Yeah, but the envelope remains the same under root of VR square plus VE square.
That's right, but therefore if VR contains noise, if VR is S sub R plus N sub R, right, then RT will be whatever that is, square of that plus square of this, that's all there. We are assuming that this contains both signal plus noise, so therefore envelope and phase are both noisy here, right? They are not the true transmitted values, they have been degraded by noise. This is a noisy envelope and this is a noisy phase, but in addition to that noisy phase, which is the effect of noise, we are assuming the presence of a phase shift theta, which is essentially to do with the fact that the transmitter and the receiver are at physically different locations, and therefore the carrier in proceeding from one place to another is associated with a time delay and therefore a phase shift, right? Is it clear? The source of this phase shift is the physical separation between the transmitter and the receiver, right? You might have transmitted the carrier with zero phase, but due to propagation delay, the received carrier will be with some non-zero phase whose value may or may not be known to you, right? In general, it is not known, but still, even though in general theta is not known, still we differentiate between two situations for demodulation, that is theta known and theta unknown. How can theta be known? This can be known provided at the receiver you have a carrier recovery circuit, a phase estimation circuit, right? If you have a carrier recovery circuit whose purpose is to find out the phase of the incoming carrier, then you can assume it to be known if it does its job properly, alright. So for the purpose of the discussion, and this is the reason I want to explain the term coherent demodulation, with which you are familiar in your analog communication courses, but I want to re-emphasize that here for us. When we talk about coherent demodulation, what we are essentially saying that theta is known to the demodulator. And how can it be known? As I said just now, maybe by a carrier recovery circuit. So which is a separate task which I will not discuss at the moment, but when we talk about coherent demodulation, it is therefore implied that we have a synchronization circuit which we call the carrier recovery circuit, whose job is to obtain the true value of theta as it is coming in. Okay. In case for some reason it is not either practical to do it or expensive to do it, right, we will have a situation where theta is not known. Suppose we have a situation where we cannot make a carrier recovery circuit work properly, therefore it is not practical to in that situation to find out the value of theta because our carrier recovery circuit does not work. Or it may turn out that we may want a very cheap implementation of the receiver in which we don't want to do a phase estimation, an extra job. Then we have the situation of what we call non-coherent demodulation. We are familiar with these terms, nothing new for you. So coherent or non-coherent has to do with a carrier phase being known or carrier phase being unknown. Now suppose theta is known, because at the moment I am discussing coherent demodulation, right? And digital communication, except for a few very special cases, most of the time we will be talking about coherent demodulation. There will be a few situations like FSK where we can talk about non-coherent demodulation, but in all other cases like various versions of PSK or combined amplitude phase shift keying, because some information is present in the phase, we just cannot afford to do non-coherent demodulation, right? Except in FSK where the information is not in phase but in frequencies, right? In that case we can think of doing non-coherent demodulation. But if the information itself is somehow embedded in the phase, either directly or implicitly, then there is no question of using non-coherent demodulation, right? So that point you must remember. Therefore, most of the cases we will be discussing the coherent demodulators here, and when theta is known, we can write the received signal in its complex form as V sub RT plus J times V sub IT. So how do I show the phase shift here in the received signal in the complex notation? Into e to the power j theta. And as I said, if it is perfectly known, I can remove the effect of e to the power j theta by simply multiplying the received signal with e to the power minus j theta, right? And from there onwards, I can assume as if I have received a signal with no phase shift. So we can as well assume theta to be 0. Okay. So if I am having a coherent demodulator based on the fact that I have a carrier recovery circuit, what basically I do is from the carrier recovery circuit I estimate the phase theta and then use that estimated phase to multiply Vt by e to the power minus j theta so as to remove the effect of theta. Somebody is talking a bit too much. Please, it disturbs me a little bit. Alright, so from here onwards I will assume that theta is 0. Okay, and of course we can do so in coherent demodulators. Now let's with this introduction to coherent demodulators, let us briefly come to alright, this is a good stopping point. We'll stop here.